Hello, algebra enthusiasts. Let's take our exponential functions to the next level and apply them to real-life situations. What we're going to talk about is a little growth and decay. So we're going to have exponential growth and we're going to have exponential decay. And we'll kind of talk about different situations in life when we'll use one or the other. Let's start with our exponential growth. It says when an initial amount increases by the same percent over a given period of time. Okay, there's a lot of cases when this happens. Your investments, bank accounts, things like that, they will increase over a given period of time. Population, all kinds of things. Okay, there's a bunch of lists of things that we could use. But there's this equation. Y equals A times the sum of 1 and R, and that is to the t power. That 1 plus R is to the t power. So Y stands for the final amount. A is your initial amount. The R is our rate of change, expressed as a decimal. So R is that rate expressed as a decimal. It'll be given as a percentage. And then T is always in years. T is always in years. So for example, if it gives you in months, put that months out of 12. Like if it said 6 months, 6 out of 12 for 0.5. Okay, so just be careful with that. We'll see some examples here. Okay, so let's try a problem. It says in 2008, the town of Flat Creek had a population of about 280,000. and a growth rate of 0.85% per year. What will be the population of Flat Creek in the year 2018? So our keywords here are, we had a growth. We had a growth. That tells me I can use my growth equation here, my exponential growth. So I got y equals, let's take back and look, y equals a times 1 plus r to the t power. So I'm trying to find what y is, right? I'm trying to find what y is. A is our initial amount, which we had 280,000. So I'll go ahead and plug that in. And then I got 1 plus r. 1 plus, well, here's my r, my rate. But just make sure rate has to be written as a decimal. Right now it's as a percent. Well, to get it as a decimal, you move it 2 to the left. Move your decimal 2 to the left. So we're going to write that as 0.0085. So 0.0085. And t is in years. And let's see, so 2018, and it began in 2008. That's a total of 10 years. So t is 10 for 10 years. And now it's about going through your order of operations. So we deal with inside the parentheses first. So I got y equals 280,000 times 1.0085 to the 10th power. And my order of operations tells me I need to do exponents before I multiply. So I need to take 1.0085 to the 10th power. And whatever you get on your calculator, just immediately take that times 280,000. I'm going to round here just so you can see 1.088, and it keeps going. And we're going to take that times 280,000 to give us 304,731 people. We're talking population. So there you go. In 10 years, at a growth rate of 0.85%, if the town's at 280,000, in 10 years it'll jump to 304,000, almost 305,000. So that's a very small increase, but over 10 years, it keeps getting compounded, so it increases faster, right? If you think about exponential growth, it increases fast, okay? That's what happens. Small percent, yet it increases by almost 25,000. So just to figure out what formula I want to use and apply it. One of our big things that we use this growth rate, our exponential growth, is for interest, okay? Because we got two types of interest. You've dealt with simple interest before. That's where you've just taken, to find the interest, you take principal times the rate times the time. Okay, very simple interest. And if I look at my simple interest equation down here, my simple interest, what happens is, after a year, let's say I have 8% interest. This is 8% interest. That's why we're multiplying by 0.08. You take your amount times 0.08 and you get $80 and you add that on. So then the next year, when you take your interest again, you do your interest on your initial amount again and you get $80. Well, you add that on to your total from the year before And so you'd be at 1160. But you're always taking the interest on your initial amount. We see that? You're always taking the interest on your initial amount and then adding that to your new amount. That's simple interest. Simple interest, if you look at our graph here, it's very constant, right? It's a constant rate of change. Well, if you're smart, you want to get an account that has compound interest, because compound is an exponential growth. It gets more and more in a hurry. And what happens is, what's the difference between compound interest, and we'll talk about the equation for that. Compound interest, right, you take your percent of your initial amount the first year. So here's your new total, 1080. Okay, well then when you take your percent for the next year, you're going to take it on your new total. So instead of going up 80, it's going to go up a little more, 8640. And then you add that onto your new total. Well, then you take the interest of that new total. So you're basically taking the interest of your new total in your account. So compound interest is much better to have than simple interest for an investment or a bank account. And look at that. It's the exact same thing as our exponential growth, but now we have to take into account how many times it's compounded a year. This n here, that's my new thing, the n. How many times it's compounded a year. If it's compounded yearly or annually, it's just once a year. So it's really the same thing as my exponential growth equation. Right? My y equals a times 1 plus r to the t. Right? If it's compounded annually or once a year, it's just that equation. But if it's compounded monthly or something else, then we got to take into account for that n, that n that we got. Otherwise, it's the exact same equation. Okay? So let's take a look at this. Their compound investment here. When Julian Lewis was born, his grandparents invested $1,000 in a fixed rate savings account at a rate of 3.5%, compounded monthly. Okay, you got to pay attention to this. Compounded monthly. That's going to affect our equation. He'll receive when he turns 18 to help with his college expenses. What amount of money will he receive from the inventor? Okay, so we're going to use our new equation here. It's really the same thing as our old one, except we got to take into the compounded monthly into effect here. So I'm going to write our equation out. A equals P times 1 plus R over N times T power to the N times T power. So we're looking for what A is. The principal we saw is $1,000 times 1 plus, well, my rate we found was 3.5%. Write that as a decimal, so move it over 2 to the left, 0.035. So 0.035 over, okay, compounded monthly now. Compounded monthly. That tells me that it gets compounded 12 times a year. So that's what my n is going to equal. So I'm going to put 0.035 over 12 to the 12 times, well, what's the time? He's 18, and it's when he was born, so 18 years. So 12 times 18. So T would be 18. Okay, so you got to take into account the compounded monthly. Now follow your order of operations. We need to do this, go inside the parentheses, take your 0.35, and divide it by 12 right away. So I'm going to replace this value with 0.0029, and you can round that one. The more digits, the better. So I'm going to go to the 10,000th here. We'll then add your parentheses. So I got 1,000 times 1.0029 to the, well, 12 times 18 gives me 216 up here. So we take 1.0029 to the 216th power, and just take that number times 1,000 on your calculator right away. I'm going to round it here though, 1.869, and we end up with $1,869.17 when I round. So there you go. They put in $1,000 at 3.5%, and when he turns 18, he almost made another $1,000 on that, right? He's going to walk out into his account at $1,869. Okay? So we just got to take into account if it says compounded, right? Because then we got to apply that n, Okay, and we also have decay, right? Might not always be a good thing with our exponential equation. So decay, the only thing that changes is we have a minus sign now. We're not going to worry about anything being compounded. And decay, the thing I always think of is if you buy a car. Right? If you buy a car today, in 20 years, it's obviously not going to be worth as much. Unless it's like a collector's edition, but that's a totally different story. But it has wear and tear, there's new models, so there's decay on cars. So the only difference is we put a minus sign in there to find its decay. It's exponential decay. So same thing. Let's write my equation down here. Y equals A times 1 minus R now to the T. Because it said estimate the amount of donations after the recession, right? It's got a recession, so it dropped. Those are my key words to know that I want to use a minus sign here, that it's got decay. So let's just plug in our information. We put in 390,000 for our initial amount times 1 minus, remember 1.1% as a decimal, move it 2 to the left, 0.011, and to the 5 years, right? 5 years it says up here. And work inside of your parentheses first. So you got 390,000, and that would be 0.989 to the 5th power. So take that to the 5th power, and immediately take that times 390,000. But I'm going to round here just to take a look. 0.946, and we end up with, should be less than our initial amount, 369,017 when I round. So there you go. They had an exponential decay. They had a decay at 1.1% a year. Okay, so let's figure out what formula you need to use by how it's worded. Read carefully whether it's growth. If it's growth, look to see if it's compounded. And if it's decay, just use the minus sign instead of the plus. That's all I got. Enjoy. Deuces.